Antimatter is not science fiction. It is not a theory from a forgotten textbook. It is real, and it exists right now in laboratories, in particle accelerators, in the quiet hum of machines that push the boundaries of what we understand about reality itself. For centuries, humanity believed everything around us, the air we breathe, the ground beneath our feet, the stars above, was made of one kind of substance: matter. Atoms, electrons, protons, neutrons. Simple, familiar, understandable. But in 1928, a British physicist named Paul Dirac looked at the equations of quantum mechanics and found something impossible. He didn't set out to rewrite physics. He was just trying to describe how electrons move at near light speeds. Yet his equation had two solutions. One matched what we knew, the electron with negative charge. The other, a particle with the same mass as an electron, but with a positive charge. No one believed him. Even Dirac himself hesitated. He called it a hole in the vacuum, a mathematical ghost. But then, in 1932, an American scientist named Carl Anderson was studying cosmic rays using a cloud chamber, a device filled with vapor that revealed the paths of charged particles. And there it was, a track, curved the wrong way, by a magnetic field. It had the mass of an electron, but moved like it carried a positive charge. Anderson had found the first antimatter particle. He called it the positron. And for the first time in human history, we knew matter has an opposite, not just in theory, in reality. The discovery of the positron changed everything. Because if an electron has an antimatter twin, then so does every other particle. The proton has its antiproton. The neutron has its antineutron. Even the neutrino has its antineutrino. And each one, identical in mass, identical in behavior, carries the exact opposite charge. This wasn't just a curiosity, it was a revelation. Physics had to be rewritten. The universe wasn't built from one kind of stuff. It was built from two mirror images, opposites, and when they meet, something extraordinary happens. When an electron collides with a positron, they vanish. Both cease to exist as particles. In their place, pure energy. Two gamma-ray photons flying off in opposite directions, carrying the full weight of Einstein's famous equation. That means even a tiny amount of antimatter can release enormous energy. 1 gram of antimatter, annihilating with 1 gram of matter, would produce an explosion equal to roughly 43 kilotons of TNT. That's more powerful than the bomb dropped on Hiroshima. And that's just 1 gram. Imagine a kilogram. A single kilogram of antimatter annihilating with a kilogram of matter would release energy equivalent to 43 megatons of TNT. That's over 800 times more powerful than the Tsar Bomba, the largest nuclear weapon ever detonated by the Soviet Union in 1961. The Tsar Bomba flattened forests 100 kilometers away. Its shockwaves circled the Earth 3 times. The light from its fireball could be seen over 1,000 kilometers away. Now imagine a bomb made not of uranium or plutonium, but of antimatter. No radioactive fallout. No long-term contamination. Just a flash. Then silence. Total destruction. And here's the terrifying part. We already know how to make it. We've done it. But making even a single atom takes billions of dollars. CERN, the European Organization for Nuclear Research, operates the world's most powerful particle accelerator, the Large Hadron Collider. Every second, it smashes protons together at nearly the speed of light. Out of trillions of collisions, maybe a few dozen produce an antiproton. To collect just 1 billionth of a gram, 1 nanogram, of antimatter, CERN runs its machines for months. And even then, storing it is nearly impossible. Because antimatter doesn't just disappear when it touches air, it disappears when it touches anything. Any container made of matter, metal, plastic, glass, will cause immediate annihilation. So scientists use magnetic traps. Superconducting magnets create invisible force fields, like a cage made of energy, that hold the antimatter suspended in a vacuum, floating in midair, never touching a single atom of normal matter. These traps are cooled to within a fraction of a degree above absolute zero. They require massive power. They need constant monitoring. And even then, some particles escape. Each year, CERN loses a portion of its stored antimatter, not because of failure, but because the universe is not built to hold it. As of 2025, the total amount of antimatter ever produced by humans is less than 20 nanograms. That's 20 billionths of a gram. Enough to power a light bulb for a few seconds. Not enough to lift a paperclip. And the cost? 1 gram of antimatter would cost approximately $62.5 trillion US dollars. That's 62,500 billion dollars. More than the entire global economy produces in a year. More than all the gold ever mined on Earth. More than the combined GDP of the United States, China, Japan, Germany, India, and Russia. We cannot afford to make a gram. We cannot afford to make a milligram. We cannot even afford to make a microgram. And yet, we do make it. Why? Because it saves lives. In hospitals across the world, thousands of patients undergo a procedure called PET scanning, positron emission tomography. It is one of the most accurate ways to detect cancer, heart disease, and neurological disorders like Alzheimer's. Here's how it works. A patient is injected with a harmless sugar solution, glucose, that has been slightly altered. One of the oxygen atoms in the glucose molecule is replaced with a radioactive isotope called fluorine-18. This isotope decays by emitting a positron, an antimatter particle. The positron travels only a few millimeters through tissue before it encounters an electron, a normal matter particle. They collide, annihilate, and produce 2 gamma rays traveling in exactly opposite directions. A ring of detectors around the patient picks up these gamma rays. A computer calculates where the collision happened and builds a detailed 3D map of metabolic activity inside the body. Cancer cells consume sugar faster than healthy ones. So when the radioactive glucose gathers in tumors, the PET scan lights them up like neon signs. Doctors don't see shapes. They see activity. They don't see lumps. They see hunger. And it all begins with a single positron, an antimatter particle, born from a lab-made isotope, traveling a fraction of a millimeter and vanishing in a flash of light that reveals the hidden enemy inside a human body. This technology has been used since the 1970s. Today, over 2 million PET scans are performed annually in the United States alone. Millions more worldwide. Antimatter isn't waiting for the future. It's already saving lives today. And yet, we still don't know why it exists at all. After the Big Bang, 13.8 billion years ago, energy condensed into particles. Matter and antimatter should have formed in perfect balance. Equal amounts. Perfect symmetry. If that were true, every particle of matter would have met its antimatter twin. They would have annihilated each other completely, leaving behind nothing but light. No stars, no planets, no people, but we exist. So something broke the symmetry. For every billion antimatter particles created in the early universe, there were 1,000,000,001 matter particles. Just one extra. That's all it took. After the mutual destruction, 1 particle of matter survived for every billion annihilations. And those survivors became everything you see, every galaxy, every mountain, every drop of water, every breath you take. We are the leftover dust from a cosmic accident. Scientists call this imbalance, baryon asymmetry, and no one knows why it happened. Some theories suggest unknown forces, undiscovered particles, or violations of physical laws we haven't yet detected. Others propose entire regions of the universe made of antimatter, hidden beyond the observable horizon. Maybe somewhere far beyond our telescopes. There are anti-stars burning, anti-planets orbiting, even anti-life thinking about whether they're the anomaly. But we have no evidence, no signals, no gamma-ray signatures from distant annihilations. So far, every observation confirms our universe is made almost entirely of matter. Why? That remains one of the greatest unsolved mysteries in physics. Meanwhile, researchers continue to study antimatter with increasing precision. At CERN, the Alpha experiment traps antihydrogen, the simplest form of antimatter made of one antiproton and one positron. They cool it to near absolute zero. They hold it for hours. They shine lasers on it. They measure its spectrum. And what do they find? So far, nothing unusual. Antihydrogen absorbs and emits light at exactly the same frequencies as regular hydrogen. Its gravitational behavior, though still being tested, appears identical. Its structure, its energy levels, its quantum properties mirror those of ordinary matter. It's not magic. It's not evil. It's not supernatural. It's just the opposite. And that's what makes it so dangerous and so fascinating. Because if antimatter behaves exactly like matter, then why did the universe choose one over the other? Could there be a version of you made of antimatter, living in a parallel universe, reading a book written in reverse, thinking the same thoughts, wondering why you're the anomaly? We don't know, but we keep looking. NASA and other space agencies have considered launching antimatter detectors into deep space, aboard satellites designed to hunt for natural sources of antimatter. Perhaps cosmic rays from distant supernovae carry traces of primordial antimatter. Perhaps pulsars or black holes produce it naturally. So far, none have been found. The most promising signal came in 2011, when the Alpha magnetic spectrometer, mounted on the International Space Station, detected a small excess of positrons in cosmic rays. Some scientists thought it might be evidence of dark matter annihilation. Others suggested it could be from pulsars, but no definitive source has been confirmed. We're still blind to the antimatter sky, and perhaps that's the point. Perhaps the universe hides antimatter not because it's rare, but because it's too dangerous to be seen. Because if we ever learn how to store large quantities, if we ever learn how to weaponize it, we would have the ultimate tool. A bomb that needs no fissile material, no enrichment plants, no nuclear reactors, just a vial of antiprotons, a single gram, a single detonation, and a city gone. No radiation left behind, just silence. And yet, we are nowhere near that. The current record for storing antimatter, about 1,000 seconds, just under 17 minutes, achieved in 2023 at CERN. Before that, it was seconds. Before that, milliseconds. We're learning how to hold a spark, not a flame. And still, we persist. Because understanding antimatter isn't just about weapons or bombs. It's about understanding the origin of everything. If we can explain why matter won, why we exist, we may unlock secrets deeper than gravity, deeper than time. We may learn whether the laws of physics are truly universal, or if they bend depending on whether you're made of matter or antimatter. We may even discover whether antimatter falls up instead of down. Yes, that's a real question. Does antimatter respond to gravity the same way as matter? Most physicists say yes, but no one has proven it. In 2023, CERN's Alpha-G experiment began dropping antihydrogen atoms in a vertical shaft, watching to see if they fall downward like normal matter or rise upward, defying gravity. The results are still pending, but if antimatter falls up, it would shatter Einstein's equivalence principle. It would mean our understanding of gravity is incomplete. It would mean the universe is stranger than we ever imagined. And if it falls down, then we're back to square one. Why did matter survive? Why are we here? The answers may lie not in grand explosions, but in the quietest places. In a vacuum chamber, in a magnetic trap, in a beam of antiprotons traveling at 99.999% the speed of light. In the space between two particles, the moment before they meet. That split second, that silent collision, that flash of light, it holds the key to why the universe exists at all. And yet, despite all this, antimatter is not a threat. Not yet. It is too rare, too expensive, too fragile. We cannot build a bomb. We cannot weaponize it. We cannot even store enough to power a flashlight for more than a few seconds. What we can do, what we're doing, is use it to heal, to see inside the human body, to find cancer before it spreads, to save lives, and perhaps, someday, to answer the oldest question of all: why are we here? Not as a species, not as biology, but as a consequence of a single, unexplained imbalance. One extra particle in the first moments after creation. We are the echo of a mistake, the result of a flaw, the last remnant of a battle fought before time had meaning. And every time a doctor uses a PET scan, every time a patient survives because of a positron's brief journey, we are reminded antimatter is not the enemy. It is not the end. It is not a weapon waiting to be unleashed. It is a mirror, and in its reflection, we see ourselves, not as gods, not as conquerors, but as survivors of a universe that almost erased us, and somehow, against all odds, let us live. We hope this journey ignited your curiosity. Stay with us as we explore the hidden architecture of reality. Subscribe and join us for the next discovery.